Here we're asked to show that for any clockwise oriented cycle on a PV plot, the net work done by the system will always be positive. So what we mean by that is clockwise oriented cycle on a PV plot. So here's our PV plot. This is clockwise oriented since we're moving in a clockwise direction. And we want to show that the net work done by the system, so by the system, will always be positive. So here we have a picture of the system, like a gas, for example, inside a piston cylinder arrangement, and it's going to exert some pressure on the surroundings. And to find the work done by the system, so a little bit of work done by the system is going to be the force dot product with the displacement, and I'm going to put it in terms of a differentially small displacement like this. This would be like ds. And the force is just going to be the pressure times the area. So we'll say this piston has some area A. So the force would be pressure times the area A, dot product with the displacement. That displacement ds, I'll just leave it as ds here. Looks like that. We can do a little bit of rearranging. That can be written, oh, by the way, these are vectors. I should be careful. Since these are vectors here, I should write these as vectors. So the force is in the I hat direction and the displace is in the I hat direction. We'll call this direction headed upward the x direction. So you can see that the displacement, I'm assuming it's going upward, that's in the positive I hat direction. The force would be the pressure times the area, which would be acting upward here, so that's in the positive I hat direction. So when we do that dot product, we'll get P times A times ds. You'll notice that the A times ds is actually a little bit of volume. So this is just P dV. So you can see that our little bit of work done by pressure forces, done by the system, is P dV. So if you want the total work done by the system, it's going to be the integral of P dV as we go from some initial volume to some final volume. Okay, so this is just a review. You've seen this sort of thing before, but I thought I'd run through it again just for reference. And the reason I wanted to do that here is because you can see that if the volume increases, so if V2 is greater than V1, so if V2 is greater than V1, then the work done by the system will be positive, right? This integral will be positive. Likewise, if V2 is less than V1, then the work done by the system will be negative. Okay, and the reason I'm showing that is because when we go back up to this plot and we have the cycle, a cycle is basically just a path that returns back to its starting point, so it's a closed loop. But if I break this up into, let's go to the smallest volume here, which would be right here, and then the largest volume would be right there, right? So if I go from this point out to this point, so if I break this up into one path going that way, you'll see that that part's an expansion. The piston here is moving upward, and the final volume, let's call this V1 and this V2. For that case, V2 clearly is greater than V1, and then we'll have the work done by the system will be positive. So let's call that path 1, and then path 2 will be this path going this way. And then work done by the system in that case will be negative because we're going, the final volume here is less than the initial volume here, and we just showed for a moment, just a moment ago, that will give you a negative. So let me just do this. So this is from 2 to 1, and this first one is from 1 to 2. Right? Now the other thing to keep in mind is that the average volume in going from 1 to 2 is larger, the average pressure from 1 to 2 is larger than the average pressure from 2 to 1, right? So that means that the magnitude of this work will be greater than the magnitude of that work. And that's, again, because the average pressure is higher than the average pressure here. Another way to look at this is just geometrically. We know that the work is since it's the integral of p dv, it's the magnitude is related to the area underneath the curve. So in going from 2 to 1, this path 2, the amount of work done, let me just highlight it, is this area underneath the curve. Right, so that is the amount of work done here as you go from 2 to 1. It's just the area under the curve. It's negative because we're going from right to left, and the final volume is smaller than the initial volume. But the magnitude is this red highlighted area there. Now the magnitude in going from V1 to V2 is larger because, again, it's the area under the curve. So let me highlight that in blue. So that'll be this area underneath the curve. So you can see the magnitude of the work going from 1 to 2 is going to be greater than the magnitude of the work going from 2 to 1. So when you add those two together, 1 to 2 plus the work done from 2 to 1, you'll see that that will be greater than 0 because this magnitude, the blue area here, is larger than that magnitude, which is the red area. The sign of this red area here is negative because the final volume is smaller than the initial volume. The sign of the work going from 1 to 2 is positive because the final volume is greater than the initial volume. And so when you add those two together, it'll be positive. So we can then conclude that the net work done in this clockwise orientation here will always be positive. Okay, we'll go ahead and end the example there.